Hello everyone, welcome to my channel, the Civil Channel 25. So in this video I am going to do a video continuation of the previous video, that is strength of materials. We have finished up to the elastic constants, that is bulk modulus. Up to bulk modulus we have finished in previous video. Now coming to the Poisson's ratio. Poisson's ratio is denoted by the symbol mu, and within the proportionality limit, Poisson's ratio is the ratio between the lateral strain and linear strain. That is, lateral strain is denoted by E lateral and linear strain is denoted by EL, E linear. That is, mu is equals to E lateral by E linear. That is, E lateral and E linear are always opposite to each other. So this E lateral is calculated with elastic constants E and mu, and this E linear is calculated with E. E is the Young's modulus, understand? And there are some range for the Poisson's ratio, that is theoretically and practically also. See, theoretically -1 less than or equal to mu less than or equal to 0.5 theoretically, and practically 0 less than or equal to mu less than or equals to 0.5. This is only for the engineering materials, understand? And these are the important thing, that is the mu value for some engineering materials. This will be asking in match the following also. See, for human tissues and naval foam, the mu is equals to -1, and for cork mu is equals to 0 always. This is very important one. For incompressible materials like rubber, wax, water, mercury and paraffin, the mu value is 0.5. And for isotropic and homogeneous materials, mu is equals to 0.25 to 0.33. And for soft metals, mu is greater than 0.25. Example, for soft metals, mild steel, mu is equals to 0.33. For brittle materials, mu is less than 0.25. Example, for concrete, mu is equals to 0.15. And for the cast iron, mu is equals to 0.23. Now coming to the relation between the elastic constants. As we have learned previously, there are 4 elastic constants, that are E, Young's modulus, and G, shear modulus, mu is Poisson's ratio, and K is bulk modulus or volume modulus. See, these are denoted by E, G, mu, K. And the first elastic constant, this is very important thing. And if we learn these formulas, we can do the problems related to this also. First one, E is equals to 2G into 1 plus mu. And second one is E is equals to 3K into 1 minus 2 mu. And third relation is mu is equals to 3K in minus 2G by 6K plus 2G. And fourth one is E is equals to 9kg by 3k plus g. These are the relationship between the elastic constants. These are very important formulas. First one, E is equals to 2g into 1 plus mu. Second one, E is equals to 3k into 1 minus 2 mu. Third one, mu is equals to 3k minus 2g by 6k plus g. Fourth one, E is equals to 9kg by 3k plus g. For example, see, coming to the formulas, how coming to the problems, how they are asked means, for example, they will be giving the Young's modulus and they will be giving the Poisson's ratio. You have to find shear modulus. So shear modulus is G. What is the formula related to these 3 elastic constants? We have to verify. E, mu and G. E, mu and G. See here, this one is the correct formula. For example, see, if they have given bulk modulus and Poisson's ratio, we have to find Young's modulus. What is the formula? We have to see these 3 elastic constants and this is the correct formula. Understand? So like this we have to do the problems on it. And next one, lower and upper limits for G and K in terms of E, shear modulus and bulk modulus in terms of Young's modulus. First one, case 1. For all engineering materials, 0 is less than or equals to mu is less than or equals to 0.5. See, for example, mu in terms of G and K we have told no, mu Poisson's ratio, Young's modulus and bulk modulus. See, if mu is 0, then G is E by 2 and K is E by 3. If mu is 0.5, then G is E by 3 and K is infinity. And in this, from this table we can tell as Poisson's ratio increases, then shear modulus decreases and bulk modulus increases. Understand? And coming to the case 2. Case 2, for isotropic and homogeneous materials, the mu range is 0.25 less than or equals to mu less than or equals to 0.33. Then mu G K. If mu is 0.25, then G is E by 2.5. Then K is 0.67 E. If mu is 0.33, G is E by 2.6 and K is E. Understand? From this table we can, for isotropic and homogeneous materials, we can tell E is greater than K is greater than G. Young's modulus is greater than, bulk modulus is greater than G. If mu is less than 1 by 3, then K is less than E. Poisson's ratio is less than 1 by 3, then bulk modulus is less than Young's modulus. If mu is 1 by 3, then K is equals to E. If mu is greater than 1 by 3, then bulk modulus is greater than E. For isotropic materials, this is E is greater than, K is greater than G. Understand? And next one, the value of any elastic constant is greater than or equals to 0. If the value of any elastic constant greater than or equals to 0, then E, G, K is greater than 0, then mu is greater than or equals to 0. Coming to the material type, total number of elastic constants and total number of independent elastic constants. This is also very important one. For homogeneous and isotropic materials, the total number of elastic constants are 4 and number of independent elastic constants are 2. Next, for homogeneous and orthotropic, the total number of elastic constants are 12 and number of independent elastic constants are 9. Coming to the homogeneous and anisotropic, total number of elastic constants are infinity and number of independent elastic constants are 21. This is very important one. Previously in many exams this question is asked. Now let us take one problem related to this. When a rod of length 150 mm and cross section of diameter 10 mm elongates by 3 mm, what is the reduction in lateral direction if mu is equals to 0.25? First we have to write what is the given data. Given data is length given 150 mm, diameter given 10 mm and elongates by delta L is equals to 3 mm, and if mu is 0.25, mu also given is equals to 0.25. First we have to take one rod. This is the rod, for example. This is the rod. This is elongating, pulling only because it elongates. This is 10 mm given as in question diameter, and this one is 150 mm length. So now we have to find reduction in lateral direction, that is delta D. We have to find. What is the formula related to delta D? Delta L D L mu. The formula is mu is equals to E lateral by E linear. That is E lateral means delta D by D and E linear is delta L by L. What is delta D here? That one only we have to find. No? Delta D by 10. Here D is 10 by here delta L 3 by 150. Understand? Is equals to mu. Mu value is 0.25 is equals to delta D by 10 into, coming to this side, 150 by 3. Here 0 0 cancel, 3 ones are 3 5s are 0.25 is equals to 5 delta D delta D is equals to 0.25 by 5, that is equals to 0.05 mm. So delta D is equals to 0.55 mm. Understand? Next one theoretical one we have to derive and tell. The ratio of Young's modulus to shear modulus of mild steel is. First one, E is Young's modulus, understand, and G is shear modulus. What is the metal given? Mild steel. As we have learned previously, the mu value for mild steel is 0.3. For concrete is 0.15. For cast iron is 0.23. What is the formula related to E, G and mu in elastic constants? E is equals to 2G into 1 plus mu. Understand? Next, taking this side. Here they are asking ratio of E and G. Means E by G we have to find. E by G is equals to 2 into 1 plus mu. E by G is equals to, here mu value is 0.3 for mild steel, no, 2 into 1 plus 0.3. So E by G is equals to 2 into 1.3. Understand? Here 2 into 1.3 is 2.3, no. E by G is equals to 2.3. So what is the given one here? The ratio of E and G is 2.3. That is ratio of Young's modulus to shear modulus is 2.3. Understand? Like if they are asking for any material, we can calculate like this. Like for mild steel, we have to remember the Poisson's ratio value is 0.3. And for concrete, the Poisson's ratio value is 0.15. And for cast iron, the Poisson's ratio value is 0.23. For cork, it is 0. Like that, we have to remember and we have to substitute that particular value in this, and we will be getting the ratio of any of the elastic constants. Understand? Like this, let us take the another one. If the modulus of elasticity for a given material is twice its modulus of rigidity, then the bulk modulus is. They are asking here to find K. So here given data is the modulus of elasticity is the twice the its modulus of rigidity, and shear modulus is same. Modulus of rigidity and shear modulus is denoted by the symbol G only. Understand? So here this statement is given in the question, and next E is equals to 2G into 1 plus mu. Here E is equals to 2G given, no. This one substitute here. 2G is equals to 2G into 1 plus mu. This one gets cancelled. Here mu is equals to, here 1, no, mu is equals to 0 we get. Understand? And next one, take another elastic constants. Like they are asking to find K, no. So E is equals to 3K into 1 minus 2 mu. Understand? So E is equals to 2G as given in the question statement. 2G is equals to 3K into 1 minus, here mu is equals to 0, no. So 2 into 0 is 0. Understand? And here 2G is equals to 3K. Understand? So K is equals to 2G by 3. So this is the bulk modulus. We can, as I have told you, shear modulus and modulus of rigidity both are denoted by G or C. So bulk modulus is 2C by 3 or 2G by 3. Understand? So this is the bulk modulus value. Next one, and coming to the elastic constant related problem. Next one is the Young's modulus and Poisson's ratio of the material are given. See, Young's modulus is denoted by E is equals to 65 kilonewton per meter square, and the Poisson's ratio mu is equals to 0.3 respectively. Then the modulus of rigidity in kilonewton per mm square is. So what is the formula related to E, mu and G? E is equals to 2G into 1 plus mu only, no. Next one E. E is given as 65 here. 65 is equals to 2G into 1 plus mu value is 0.3. So 65 is equals to G into 1 plus 0.3 is 1.3. Understand? So 65 is equals to 1.3 into 2 is 2.6 G. So G is equals to 65 by 2.6. That is equals to 25. G is equals to 25 kilonewton per mm square. Understand? This is the value of the modulus of rigidity in kilonewton per mm square.